Right. Okay, so I would like to start by talking about chemistry. Chemistry is about building molecules, making molecules. And in general, in a chemical reaction, we start with, say, an ensemble of A and an ensemble of B. And through stochastic encounters of the atoms, then we end up with molecule AB. We want to put a lot more control in this chemical reaction. In particular, we want to kind of go to the limit where we can start with exactly one atom and exactly one atom of A and one atom of B and make a molecule out of these. And ultimately, we want to assemble ultra-cold molecule atom by atom with full quantum control. So the game plan for us here is to start, in our case, we work with sodium and cesium atoms and make them into molecules by starting trapping single atoms, put them in the same traps, ultimately, and zap it with a photon to make molecules. To trap single atoms, we follow the pioneering work of Philippe Grandier, where you could just shine a tightly focused beam into a chamber overlapping with the MOT and grab single atom out of it. And there's many groups, I'm sorry that I already see there are people here that I'm not listing here that are working with single atoms. And earlier in the conference, you heard the beautiful work of Broadway and Lucan, where you can also have a large array of these atoms and sort it in a highly ordered fashion in 1D, 2D, and 3 dimension. We extend such a work to be able to manipulate 2 different species. In our case, we use 2 different wavelengths. Atoms have different polarizability, 2 different wavelengths to control the different species of atoms. We can shine these 2 different wavelengths, again overlapping with MOT, to get single atoms, single sodium and single cesium. These 2 images, actually, if you look like this, they're in the same field of view. We repeat the experiment many times, and more than 50% times of the time that we actually get a single sodium and single cesium side by side that are separated by about a few microns. So from the point of view of making molecules, these atoms are miles apart. They're really in the lonely atom clubs. And to really bring them into a molecular state, we first need to put them into the same place. So what we do is, these are images of optical tweezers. We can steer the beams to just move one overlapping with the other, and then do our experiment, make molecule, or do anything that we are interested in doing with 2 atoms together, and then we separate them again for imaging. So when we detect them, they're always separated again. So now with 2 atoms in the same optical tweezer, we can begin to study their collisions. So here is the collision of 2 atoms. Through a collision, it turns out we actually won't have reactions, and that is to make a molecule. And the reason is that it's very difficult to you have to simultaneously fulfill conservation of energy and momentum to be able to have 2 things come together and stick to make a molecule. So in general, the way to make molecule, you would be through 3-body collision or through a supply of a photon to either extract or supply energy. Okay, but these molecules have internal structures, so if they are in some spin composition, they can collide, and they can have spin-changing collision such that this is enough energy for them to be ejected out of the trap and for us to see them as lost and for us to see evidence of these collisions. Okay, so the nice thing about these sort of test tube system is that we have these whole microscopic detection where we can have the full counting statistics. Not only we know what we have loaded, for example, we post-select on a situation where we have 2 atoms. After some time, collision happens either through collision with background gas, you end up with 1 atom, or collision through these kind of spin-changing collision, or molecule formation due to zapping with the light. Then you could end up with no atoms. So we can do this kind of study. I won't really want to go into detail of all the different scenarios that we can study, other than to say that in the case where we have a mixed hyperfine state, then we have the very fast time scale, 8 milliseconds in this time scale, to see these type of loss. The punchline here is to say that 2 atoms are already sufficient to see collision, and we're interested in put 3, and also in the future, we're aiming for to do 2 or 3 exact number of initial conditions to see these collision with molecules. Okay, so now there's another red line here is if we were now prepare molecule in a low hyperfine state, they can live about a second. It turns out this limit is due to the off-resonant excitation of, again, spin flipping. Okay, so, but it's long enough for us to try to make molecules. To make molecules, we'll use photo association, and it's being worked on decades in this field, where we can use light to carry away the binding energy, excite a pair of atoms into a molecular excited state. They live there transiently, and it's a non-coherent process, so ultimately they fall into multiple final states. In our particular scenario, we have sodium and cesium. So we shine laser light to the electronic excited state of the molecule near the electronic excited state of cesium asymptote. We scan these lasers, and this is what we see. So again, we can post-select on what we have loaded initially. So do all these experiments repeatedly with a scanning of a laser beam. If we start over here, we have either just sodium or cesium loaded initially. Exposing to this light doesn't really cause any depletion of the atom population. However, if we start with both sodium and cesium loaded into the tweezer as our initial condition, and you can see these lines, these simultaneous loss of sodium and cesium, they are actually molecular resonances. We can identify them. Some of them have been seen previously in Nick Biglow's group at Rochester, where they studied the photoassociation of sodium and cesium out of MOT and through ionization detection. We can see those lines and some of the new vibrational series out of those, and also additional vibrational series associated with different electronic states. So this very high signal to noise loss, simultaneous loss signal can actually be beneficial and allow us to discover previously unseen photo association line. And because we prepare 2 atoms in this optical tweezer, every time we shine a laser at the molecular resonance, we can make a single molecule. So A plus B goes to AB. We were quite flattered that our apparatus was deemed marketable for a magazine, and also that it was fascinated by the general public because it's actually easy to comprehend. Me being in the chemistry department, I have a lot of opportunity to talk to people who are working in very different fields, and it's very easy to explain our experiment, and I'm sure when I explain it, they had this picture in mind, just tweezers of atoms and stick them together. Okay, so our work, actually, I want to go back to talk about motivation. Our work was actually originally motivated by aiming for application to quantum simulation and quantum computing with polar molecules. And as already discussed in Ed Hines and John Doyle's talks earlier in the conference, that this has long been recognized in the field. But if you really want to do an experiment aiming for these applications, well, you will find that the set of tools that we have is not sufficient, because what we really want is a high, if you have a gas of molecule, you load it into optical lattices, you want high lattice filling, where you want some highly ordered atomic array. And you will also want to have single molecule control and addressability for these type of application. So our experiment was designed when I started out at Harvard 5 years ago to really aim at being able to provide these necessary tools for these applications. So our choice of sodium and cesium molecule was based on that it has a very large dipole moment in the low vibrational ground state, and that they can interact strongly, say, at 1 micron apart. Their interaction will be on the order of kilohertz or a few kilohertz. I wanted to dwell on this application a little bit more, and in fact, I wanted to say that similar to this amazing and wonderful experiment that you heard from John Doyle on the sort of 2 orders of magnitude better precision in the last decade on the constraint the electron-electric dipole moment. It is really enabled by the fact that molecules are perfect laboratory. Molecules, it's complex enough such that, in a laboratory, you couldn't just apply more than, say, 100 kilovolts per centimeter and not worry about, leakage current and systematic error. In a molecule, you could apply, say, in their case, maybe 10 volts or 1 volt per centimeter and allow you even 5 orders of magnitude enhancement of electric fields that you could ever achieve in a typical laboratory setting. In addition, molecule has these complex internal structure that allow you to do systematic checks. So you can see, what happened when you flip the electric field versus the magnetic field. You don't actually necessarily have to do that in the laboratory. You can just prepare them in different molecular states, and these states are symmetric, but pointing to different directions allow you to have very, very high rejection systematic check. So I would say the same would be for other applications such as qubits for gates and entanglement. You have these kind of competing requirements. You want to have your perfect qubit to have long coherence time to have for storage. And at the same time, you want them to interact strongly. How do you really achieve that? Well, in a molecule, you have many degrees of freedom. You have vibration, rotation, hyperfine. Let's say we can use nucleus spins of the molecule for storage, and we can use rotation degrees of freedom to achieve strong interactions. And these are not actually just isolated degrees of freedom. They are coupled through intrinsic molecular coupling. So you can transfer information from one to the other just through state preparations. And of course, you've seen that neutral atom scalability is great. You've seen large number of atoms in optical lattices or large arrays of atoms. You can do the same for these neutral molecules. So it's very promising for scalability. So we thought a lot about these directions, and one of the goals is to be able to achieve very high fidelity of, say, 2 qubit gates with molecule, aiming for 99.99 above 99.99% to hit the threshold of error correction. Most of the proposal previously, when you think about molecule to utilize the dipole-dipole interaction, you often think in terms of you need some kind of polarizing field to achieve that. But in reality, experimentally, you actually want to avoid these DC electric field or any dressing field to polarize your molecule. And the fact is because the dipole-dipole interaction in that scale comparison is much smaller than Stark energy. And therefore, it's actually imposed a lot of constraint on field stability. So if you can relax that constraint by using resonant dipole, as I've shown here, no electric field, no dressing field, then you can really remove that implementation complexity and qubit decoherence. Okay, so our proposal here and analysis was motivated by the work of Demlin, Lukin, Ray, and Gorshkov, and also experimental work in Gila Karabi and Martin Sverlein's group, where what we're thinking about here is that we want to use nucleus spin states as our qubit states, 0 and 1, but we want them to interact. So how do we do that? We allow them to interact by a pi pulse one of the states to a rotational excited state, and then we allow these resonant dipolar interaction to happen, and for a fixed amount of time, then we can, again, bring the population back, pi pulse it back down, so this become a state transfer problems. And all the states that we've chosen here are field insensitive. Turns out these molecules are closed shells, the electrons are completely paired, so there is no electron there's no electron spin, total electron spin in the molecule, so all these states are nucleus spin states. Therefore, they're long-lived, and these, again, this exchange interaction happen at 0 electric field. So the broader picture we're thinking about is that an array of molecules, we can bring out the ones that we want to make, we can bring out the ones that we want to in this gate zone to allow these to operate, and while Stark shifted using tweezer beam the interacting states away such that they can stay in their long-lived coherent states while they're not being they're not in the for participating in the gate. Okay, so for a molecule, it's very nice. We can easily find these 3 levels, but in terms of what is the feasibility, we look at the molecule in its full complexity. So the real picture is that we don't just have 3 levels. In the ground state, we have 32 levels, and in the excited state, we have more than 100 levels. So how do we, what constraint does that pose? Well, so just starting from the top, so we can bring these 2 molecules close by, allow exchange interaction on the order of 50 microseconds. Okay, but it's not good enough, although the fidelity could still be pretty high, 99.6% at some reasonable magnetic field. And this is limited by off-resonant excitation, and this is limited by that there are so many other states nearby. So what do? We can just slow things down. Actually, that makes technical implementation also easier, a lot insensitive to a lot of the control of field stability. So we can slow it down. We have to have 2 pi pulses and an exchange interaction, and each takes about a few milliseconds. And if we just allow things to process slow enough, then we can have more than 99.99% at really low magnetic field, say the Gauss. We only explore low magnetic field. Things are going to be better at high field, but we wanted to keep the ultimately experiment simple. So this calculation, and then and also many other things that we consider, including light shift of trapping from the tweezer for both the rotation ground and rotation excited. We can cancel out. We can have these magic trapping condition by turning into elliptical polarization of a particular angle, and that paper was published recently in Optics Express. Okay, so. So anyway, we analyzed a lot of different possible things that could break the 99.99%, but we think it's very feasible because the complexity of the molecule allows us to really relax the technical constraints. Okay, so to make molecules, going back to the story about making molecules, I've shown you previously about photo association. But for these applications, quantum simulation and quantum computing, we want the molecule to be in a single quantum state, okay? We want them to be in a single quantum state, and this actually had been worked out previously by the Gilla KRB group, Innsbruck, and many other groups around the world. So the way to do it is to use a coherent transfer technique. You start with a single initial state, you end up with a single final state by a coherent drive between the 2 laser beams in a well-defined fashion. Okay, so we're working toward that to start with preparing atoms in a single quantum state, single internal emotional quantum state. We use Raman sideband coolings. And we can achieve Cesium sideband 3D ground state preparation of 96%. Sodium's was a bit harder because of the system being outside the Lamb-Dickey regime, but we can also achieve a very high ground state preparation of roughly 34%. Now we can, they're prepared in the ground state separately. We need to move them, transport it to in the same place. So here is kind of a potential landscape, what we do to be able to bring the 2 atoms in the same place without any motional heating. And we do this by making sure there is no symmetric double well such that the adiabatic time scale will be forever and you cannot meet. Okay, so there's always some kind of asymmetric between the 2, but they would look different for sodium and cesium. And after the merge, if we merge or if we don't, we found that there is no heating. I wanted to quickly mention that similar work was done in Wuhan. They showed a poster yesterday where they can work with 2 different isotopes of rubidium, achieving very similar condition. Okay, so onto coherent molecular formation. We have now prepared individual 2 different atoms in their trapped ground state to make a molecule
maybe this is a better picture, in the motional ground state, to make a molecule, we need to bring them much, much closer. And in that case, you can see that the wave function mismatch is very, very large. So to do it, we have to bridge it with the least bound state. And traditionally, people do it with the Feshbach resonance. In our case, we want to use a more general technique where we want to use optical route to be able to transfer these atoms into molecule and hopefully be able to apply to a larger range of atomic species. So some reference down here, but just briefly, we found that because these two levels are very close by, but the Frank-Condon factors are very large in mismatch, therefore we have to detune. We found a scheme where we had to detune very far from the threshold. And actually, in fact, we used the ground state of a particular electronic potential, detune from there, and do Raman transfer, and we should be able to achieve sort of less than 2% spontaneous emission. Okay, so preliminary, we have done that. There's a lot of spectroscopy involved, but we were able to located this level, detune from there by right now 1.5 gigahertz. We found the state to be about 300 megahertz bound, and you can see these simultaneously lost. These line widths are actually quite sensitive, depends on all the, again, technical things, stark shift of the laser beams that we use to drive the transition, as well as the tweezer, the light that traps the atom and the molecule. So to summarize, about building single molecule. I've shown you the scheme, and I believe molecular complexity can really fulfill our wish list for quantum simulation computing. I show you proof of principle that we can build single molecule out of single atoms and preliminary some coherent transfer. Along the way, we were able to kind of stumble into a new paradigm where we can have collision study of exact number of participant preparation. So with that, I wanted to acknowledge the people who did the work. John Hood, who is actually here in this conference. Hopefully you had a chance to talk to him. He was largely responsible for these molecular transfer that I've shown you. And Lee, who's my first graduate student, built up the experiment, and Itao, who is also a wizard on these experiments. And I'd like to thank you for your attention.